figured out how to make the slide advance mechanism work.
Thank you.
Good. Thank you.
Good morning. Thanks for coming. Thanks for being here. Thanks for your support. I'm going to talk about some technology work, in particular nanotechnology work that we're doing in my group. But I want to just start off with a brief introduction into what I would like to characterize as sort of the Berkeley vision for nanotechnology. And then show you one example of that, which is the work going on in my own research group. The thing that is really fueling the tremendous interest and excitement in the field of nanotechnology, nanoscience, and nanoengineering these days, I'd like to characterize in the following way. Actually, over the last 20 years at least, many of us have been working in a field that we now understand to be called nanotechnology. We didn't call it that 20 years ago, but we've been working and manipulating materials at the nanoscale for many years in rather isolated individual disciplines. So engineers have been making nanostructures by lithography, and chemists have been building nanostructured organic and inorganic materials by chemical synthesis techniques. Of course, there's been an explosion in molecular and cell biology in this same time frame. And similarly, the sort of instrumentation physicists developed scanning probe microscopy and then scanning probe manipulation of individual atoms. You've all seen the beautiful examples of pushing individual atoms around to form man-made structures are literally on the atom-by-atom scale with scanning probe devices. All this has been going on in relatively an isolated fashion within these individual disciplines. Within the last, say, 5 years or so, there's been a recognition of the fact that in these different disciplines, the researchers, scientists, and more recently even engineers are developing the ability to manipulate matter on a similar size scale with very different techniques, and a level of sophistication of control has emerged such that people from other disciplines can begin to practice the techniques developed in other disciplines. That actually is that's really what I would characterize as the breakthrough of the last few years, is the crossing of boundaries. And that's enabled by the level of sophistication and development of these techniques, that they've become accessible to non-experts. That makes possible a really exciting new vision, which is sort of integrating these technologies together. And really the next big thing in nano is this idea of integration. The notion that you could think about designing and building systems in which you have, wet, gray, gooey stuff, biological material, that is integrated with either organic, polymers synthesized for those special purposes, inorganic, nano crystals, nano wires, nano dots, and even more complicated structures, on top of maybe a CMOS-like nanoelectronic information technology substrate layer, to build really, dramatically new devices. And that is the fuel behind really the energy in the field in general, and specifically that's the vision that's really fueling the Berkeley vision for nanotechnology moving forward. One of the manifestations of that is a project at Lawrence Berkeley Laboratory called the Molecular Foundry, in which a brand new building is being constructed for this wide array of technologies to be integrated together into one building and to be made available as a user facility to users that come from anywhere around the world. Now, similarly, that's the agenda that's fueling the construction of the new CITRIS laboratories, the new CITRIS replacement for our microfabrication, or the evolution of our microfabrication laboratory in Corey Hall to be in the new CITRIS building, and the Stanley Hall construction that's going on right now. So it's really a very exciting time in this field where we're really trying to put these things together. And here are just some images that show these things, just to illustrate. This is a carbon nanotube. I will concentrate in the rest of this talk on carbon nanotubes. We've got nano MOSFETs that we've been making here in the Berkeley Device Group, dendritic polymers, DNA synthesis with attached special molecules, either organic or inorganic nanocrystals attached to DNA. Here's some examples of some nanocrystals, proteins. Here's atomic resolution microscopes pushing atoms around. All of these different building blocks come together now in an integrated laboratory, in an integrated fashion. Now, I want to focus on carbon nanotubes because what I want to do is share with you some results recently that came from my own research group, in which we've been starting to get into this integration business. Carbon nanotubes are an example of what I call bottom-up synthesis. So let me just back up for a second and first contrast what top-down synthesis is. Top-down synthesis has to do with the way we manufacture integrated circuits today. Designers design a pattern, we make masks, we do lithography, we do etching. That's sort of the top-down approach. Now, the bottom-up approach to making nanostructures is the one in which sort of natural processes self-assemble matter on the nanoscale without the deliberate action of, say, a beam or a probe. So carbon nanotubes are an example. They naturally form in chemical synthetic processes to form these very perfect single molecules of pure carbon that have huge size from the molecular scale, a whole nanometer across, many, many carbon atoms arranged in this. It's sort of like a chicken wire, one-dimensional chicken wire shape that's rolled up together into a tube. And these have captivated the imagination of lots of researchers recently. They have remarkable properties. Here are some of the best recent results on the electronic properties of carbon nanotubes. This is a carbon nanotube transistor made by my collaborator, Hung-Ji Dai at Stanford, his group, in which they've actually been able to fabricate these into a top-gated FET structure with a high dielectric constant gate dielectric, zirconium oxide, a 2-micron gate length, and they're switching up to 7 microamps in an individual 1 nanometer diameter tube for really a kind of a world record type of transconductance, 12 microsiemens. They've demonstrated both N-type and P-type carbon nanotube transistors, and here's even an inverter that they made in which the connections were done by external wires. So this is not a monolithically integrated circuit yet, but it does show inverter action, so it works as a digital circuit. So one great interest in these carbon nanotubes is as a high-performance alternative to silicon FETs. These have very high performance, but the jury's out yet on whether or not they really, will offer enough advantage over silicon CMOS to be a substitute or a replacement. There's a lot of technology development and process issues that really become involved in that. It's a complicated story. On the other hand, there's some unique applications for carbon nanotubes, which is probably where at least let's put it this way, the first applications are likely to arise. Here's a proposal for a very dense crossbar array made with carbon nanotubes, where so here you have suspended carbon nanotubes in a crossbar, and they have remarkable mechanical properties. They can be made to bend down and touch. And in principle, since these tubes are a nanometer in diameter, this array could have extremely high density. And 1 bit is stored in the mechanical touching, the mechanical difference. The difference in, basically, it's a mechanical switch. So you store a bit based on whether or not you have a contact here here is a contact, here no contact, and this group at Harvard demonstrated a rather dramatic difference in resistance between the on and the off state in a non-optimized experiment, but showing clearly the principle. So very high density memory arrays might be possible using carbon nanotubes. Here's an even more interesting one, I think, in terms of mechanical, a mechanical device, a NEMS device, nanomechanical device. This is work from my colleague again, Hung-Ji Dai at Stanford. They grew a carbon nanotube across a little gap between a polysilicon cantilever and the substrate. Here's schematically, there's the nanotube stretching across. Here you can see it in the scanning electron micrograph. Here's a blow-up. You can see that carbon nanotube bridging across. And by applying electrostatic force to the cantilever, you can then change the force or stretch that wire. And these then have a mechanical resonance of a stretched nanoscale string, which could be in as high as 100 gigahertz. And more recent work than this shows that there is a significant piezo resistance in these carbon nanotubes, so it's relatively easy to sense that high frequency motion by measuring the voltage drop across the tube for a constant current. So one can imagine integrated nanoresonators with extremely high frequency, and imagine using these, and you can even tune them then by varying the stress by pulling on that cantilever. These also are extremely sensitive to molecules bound to the surface. Other researchers have shown that you can decorate the carbon nanotubes with specific bonding sites that make the electrical resistance of a tube sensitive to the bonding of a particular antigen or a particular small molecule. So you can make very selective, very ultra-high sensitivity sensors with carbon nanotubes. So there's all kinds of interesting applications that are being looked at. And what we decided to do in my group was to say, well, probably the way that we're going to enable most or many of these applications is to figure out how to integrate carbon nanotubes directly onto silicon CMOS. And so we started a project to tackle that issue, namely monolithic integration of carbon nanotube electronics with silicon CMOS electronics. And this is done in collaboration with Hung-Ji Dai at Stanford, who's the expert in carbon nanotube synthesis at specific locations, such as the ones I just showed. And this work, by the way, is funded by Marco and DARPA. So the idea of the experiment was to just do a first demonstration that it could, of how to do this, that it would be possible. And we tried to do it on large scale. So the idea is not to integrate one silicon transistor with one carbon nanotube transistor, but to actually build at least a medium scale integrated circuit. The issue is the process integration is not trivial. Carbon nanotubes are grown at rather high temperature. And so what we really are tackling is the process integration of how to get those nanotubes onto a CMOS chip without ruining the silicon transistors. We picked as a circuit vehicle a test chip which would allow us to use an NMOS switching array to simultaneous and grow carbon nanotubes at thousands of sites on a chip. And basically what this chip is 2,000 carbon nanotube experiments on a single chip. And we use the silicon NMOS transistor tree to act as the switch that allows us to individually switch and measure as many as 2,000 individual carbon nanotube devices on a single chip. So we're trying to integrate a chemical vapor deposition process that allows pattern placement of carbon nanotubes at desired locations with a silicon CMOS chip, and how to get that 800 or 900 degree deposition step onto that chip is the most difficult part of the project. Since we can't possibly do that on a fully finished foundry CMOS chip, we had to get control of the process and insert the carbon nanotube deposition step intermediate in the process. So this is why it's absolutely crucial for us to have CMOS capability in our lab. it's not good enough for us to just get access to industry like MOSIS, foundry type CMOS. In order to really make progress in this field of integrating silicon electronics with any kind of nanotechnology, the ability to have in our own microlab CMOS capability is crucial. We have a baseline 1 micron process that we can have access to in the microlab, and that's the one we're using. And the key place we had to focus our attention was on getting a good metal interconnect that would allow us to interconnect together large number of silicon transistors, as well as getting good contact between silicon and carbon nanotubes, and make that integrate with the nanotube synthesis. This is a picture of what this circuit looks like. It's a photomicrograph of one of our chips. It's simply, this just shows a few elements in the array. It's simply an array, a tree-like structured. Basically, it's like a memory address decoder for one side of a memory, either DRAM or SRAM type circuit. We don't have a two-dimensional array. We just have a single tree, a single address decoder. And at the nodes, at each terminal node, instead of driving a word line or sensing a bit line, or vice versa, we grow a single carbon nanotube at each of these nodes, spanning across one of these nodes across to a common electrode. And then by manipulating the address lines, 11 address lines to control 2,000 growth sites, we can then individually measure the carbon nanotube device characteristics in series with this low, relatively high performance, not the best, it's not the greatest state of the art, but good enough, through the series connection of 11 NMOS transistors. There's a single common backgate that goes underneath all the carbon nanotubes so that we can actually operate each site as a 3-terminal carbon nanotube FET. So that's the circuit vehicle. There are about 4,000 NMOS transistors on this chip. And as I say, if we get good yield of carbon nanotube growth, we would have up to 2,000 carbon nanotubes. So it's a pretty large-scale integrated circuit for this. It's the biggest chip that's been made in the micro lab in at least 20 years. Long ago, the circuit researchers here at Berkeley abandoned using our microlab to do circuit research in favor of gaining access to foundries. So nobody makes large circuits like this anymore in our microlab, and we're very proud of the fact that we actually are, and especially the microlab staff is proud of the fact that we are able to get pretty good yield on a 4,000 transistor medium scale integrated circuit in our own lab. Good. Okay, this just shows a blow up of the layout of the business side of the layout, where we have the last terminal of that tree. The red gap here is essentially an oxide film with polysilicon gate underneath it to act as a gate for a carbon nanotube that is catalyzed to grow from this point and span across this gap and connect to the interconnect metal on the other side here. Here's a photograph of a working chip. This is that growth site that I showed you. This is an example of a few of them. The tubes grow across from this metal electrode to that one. I haven't really told you how we solved the process integration problem. We use molybdenum interconnect metal, and there's a few other tricks which people have questions. I'd be happy to fill you in on the details. Here's a carbon nanotube growing across that approximately 3 micron gap. And this work was published in the January issue of Nano Letters. We have successfully gotten carbon nanotubes to grow on these sites, and our chips have hundreds so far of carbon nanotube sites that are working. And here's just an example of some current voltage characteristics measured on our chip. This is an ambipolar type of carbon nanotube, which occurs when you have small gap tubes. So it actually switches both for positive and negative gate bias with an on-off ratio of about 2,000. Here's a P-type carbon nanotube transistor, which only operates for negative gate bias. And we see just an array of different types of these tubes on the same chip under the same growth conditions. And that's really what the purpose of this chip is to allow us to gather large amounts of statistical data on what distribution of tubes that we see. That's feedback to the growth guys to help optimize the growth conditions to increase the yield of one particular flavor of carbon nanotube over another. I'm not going to go through this, but this is a table showing the kind of data that we get, sort of percentage of different sites that we see, how many sites have particular types, and so forth. And we've grown at different growth temperatures and gotten all kinds of great statistical data like this. So I'm going to wrap up and summarize. I've shown you just one example of this notion of integrating nanotechnology with CMOS technology, and there's lots more to do here. I start with a quote. This is the title of an article that's actually based on a lecture Richard Feynman gave in 1959. Anybody who works in this field knows this paper by heart. It's sort of the manifesto for today's nanotechnology. And the fact that Feynman thought this up in 1959, you know, it's Feynman. What are you going to say? It took us, you know, 40 years to realize this vision of his, more or less. Actually, in that article, he laid down a challenge and offered a prize to anyone who could write a certain page of text. I forget what it was, in a certain size. That prize was awarded to Fabian Pease at Stanford in, I think, the early 90s. So we're catching up to Feynman. Really, the frontier now is we've gotten good at doing manipulation of matter, both in the bottom-up and the top-down fashion, down to the sort of sub-10 nanometer scale. Now the frontier is integration. Really, where the excitement happens now is at the interfaces of disciplines in terms of integrating these technologies together, and especially figuring out how to interface the bottom-up, the new bottom-up synthesis methods with the existing infrastructure for information technology that we use, which is based on top-down CMOS. So again, we really want to learn how to build not just carbon nanotubes, but the wide variety of biological-based and organic synthesis-based nanostructures on top of CMOS. So that kind of leaves me with my theme that I want to leave you with, that sort of I'm not trying to represent myself as a replacement in any sort of fashion for Feynman, but, you know, 40 years later, we can move a little bit beyond where Feynman was sending us. And really where we are concentrating our effort right now is kind of in that middle, in that integration of the top-down and the bottom-up. So thank you for your time and attention. I'll be happy to answer questions.
One question, if there is one, that's about what we have time for. You'll be here for lunch, hopefully?
Yeah, I'll stay
Great.
for lunch.
Great. Yes, a question.
What is the history when you are growing and then shrinking?
When you are growing and when you're shrinking. Maybe I'm not catching your...
When you are growing, you are creating an impulse.
You're talking about the tube? Yes. Well, the tube is fixed. Once it grows across and makes contact, it then is basically fixed in place. So the switching behavior is not a mechanical switching in the experiments I showed you. It's actually a field effect. So they're acting like a field effect transistor, and a gate potential is changing the charge density inside that conducting tube.
Come close, you can switch back and forth thanks to the field effect.
It's really just the same switching. The data that I showed is the same switching mechanism that occurs in a silicon transistor. There's no mechanical movement at all. These devices, the carbon nanotubes, are semiconducting, and the application of a gate potential is changing. What's moving is electrons. Now, it is possible to make mechanical switches, and in that case, we would rely on hysteresis to make a bistable memory device. That's not the basis of the data that I showed you in our integrated chip, not yet. We are interested in going to that next step and building mechanical-based, nanomechanical carbon nanotube-based switches integrated on CMOS. That's our next thing. We haven't done that yet.
Okay, great. Thanks, Jeff.